So the title of my presentation is A Block Building Constraint Programming Model for the Container Loading Problem. My supervisors are Kate Smith-Miles and Alison Costa from Melbourne University and Optima, and also Tony from KU Leuven. Okay, so just a little bit about myself. So I am a joint PhD student with the University of Melbourne and KU Leuven. I started in March 2021, and I actually just submitted my thesis a couple of days ago. So my thesis is titled Instance Space Analysis for Cutting and Packing Mathematical Models. So yes, very nice. So today I'll be presenting some of my work that I've done in a thesis. So this is not technically a completion seminar, but it's just presenting some of my work. Okay, so yes. So I'll just state that during my PhD, I have, with my supervisors, written 2 papers. So the first one is titled Instance Space Analysis for 2D Bin Packing Mathematical Models, which was submitted to EJOR, European Journal of Operational Research. And there's a QR code up here for the first paper if you're interested in having a look. But today I will not be talking about the first paper. I'll be talking about the second one, which is the title of the presentation, which was submitted to the Computers and Operations Research Journal, which is currently still under revision, second revision. So yes, I will present the main findings of the second paper, but I probably won't have time to talk about everything that's in there. So I'll just focus on the most important parts. So, all right, so why would it be interested in container loading? So let's have some motivation. So the container loading problem and related 3D cutting and packing problems are crucial to many industries. For example, logistics, warehousing, and shipping. And essentially, we want to make sure that if you have a container, you want to fill it up with as many boxes as possible. So for example, in delivery or in shipping, you want to use containers as efficiently as possible to minimize costs. So yes, container loading is quite important in practice. And yeah, so what is it specifically? So yes, the container loading problem, which I've shortened to CLP because I'll be using that phrase quite a lot during this talk, is a combinatorial optimization problem. And it involves packing a set of smaller boxes, which are smaller boxes into a single larger container. And the boxes and the containers are all rectangular cuboids. So yes, I'll just state that the sizes of the boxes and the container are fixed, and as is the number of boxes available. So there's a limited number of boxes that you can choose from. And the objective function that we're trying to maximize is the volume occupancy, which is the proportion of the container's volume that is occupied by boxes. Sometimes we also call this the volume utilization, but yes, volume occupancy or volume utilization. So for some instances, it may be impossible to fit every box into the container, in which case you want to fit as many boxes into the container as possible, or more specifically, fit as much volume into the container as possible. So for anyone who's seen the knapsack problem before, it's quite analogous to the knapsack problem, although in this case, the profit of a box is always equal or proportional to its volume, whereas in the knapsack problem, the volumes and weights are not a fixed ratio, usually. So yeah. All right, so that's the container loading problem in general, but sometimes we want to apply additional constraints because in practice, you can't just necessarily put boxes in any way you want. So here are 2 examples of practical constraints that I will be covering in this talk. So orientation constraints specify which box rotations are allowed. So for example, if you look at figure 3, these are 2 possible orientations of a box. And the left orientation, if you imagine this is on the ground, will be quite stable, but the one on the right can easily fall over if the truck has to make a sudden stop or something, or if there's a lot of wind, then it can quite easily fall over. So it's possible, depending on the instance and the application, maybe you would say that the left orientation is allowed, but the right orientation is maybe disallowed. Or maybe you allow it, but yeah, depends on the context and the instance. So I'll also briefly just talk about vertical support constraints as well. So vertical support constraints ensure that every box is supported by either the base of the container, so it could either be basically on the floor, or it could be supported by the tops of other boxes, but it can't. Essentially, what it's saying is boxes can't just float in space if we're enforcing these constraints. And if you imagine the effect of gravity on boxes, then you can see why that might be quite relevant in practice. So these are not the only practical constraints that come up. There are also other constraints. And there's this survey paper by Bortfeld, which provides a comprehensive review of a lot of different types of constraints that are considered in the literature. And some of them include, for example, weight limits, weight distribution, loading priorities, horizontal stability. So yeah, you want to make, and sometimes you need some weight balancing. So you can't have one side of the container too heavy compared to the others. But we won't be considering those in this talk. There's just too many possible constraints, and we won't be talking about all of them. So yes, so a little bit more housekeeping before I get started with talking about constraint programming models. So I'll just mention that instances of the container loading problem are characterized into three different categories. So they are called homogeneous if all the small boxes are identical. And we'll call them weakly heterogeneous if there are only a few different types of boxes. And then strongly heterogeneous instances have very different boxes, so a lot of different types of boxes. And yes, so as you can tell, it's easy to tell when an instance is homogeneous. All the boxes are identical, there's only one type of box. But distinguishing between weakly and strongly heterogeneous instances is quite arbitrary. Usually in the literature, we designate instances with less than 20 box types as weakly heterogeneous, and then instances with 30 or more box types as strongly heterogeneous. But this is just kind of a convention. There's no hard and fast rule about it. So yeah. And I'll just mention that mathematically, an instance of the container loading problem can be described by the following data. So LWH are the dimensions of the container in all three dimensions. N is the number of different box types. So if it's one, then it's a homogeneous instance. So for each of the n different box types, we need to also specify the dimensions of the box type. So LW and H, I. And also di is the number of boxes available for each box type. So it's a limited number of boxes. We don't have an infinite number of boxes of each type available. And then Ri is a set of allowed orientations. So we do choose to enforce orientation constraints. We don't just allow any rotation necessarily. And so there for every box, there are 6 possible rotations, and Ri specifies for box type I which ones are allowed. So so each box type has 6 different possible orientations, depending on how you decide to rotate them. And I just enumerated them here, but don't worry too much about these. They are not too important. Okay, so what is constraint optimization? So now, given a set of decision variables with specified domains and a set of constraints on the decision variables, and I'll also have an objective function that I want to maximize or minimize. So in the case of container loading problem, it's usually trying to maximize the volume occupied by boxes. So anyway, the goal of constraint optimization is to assign values to the decision variables. While ensuring that all constraints are satisfied, and we also want to optimize the objective function. So yeah, depending on whether it's a maximization or minimization problem, we either want to maximize or minimize the objective function. Okay, so in this model, this is what we will present. So I'll present a seat what I call the CPA model, which is kind of a baseline constraint programming model formulation of the container loading problem. After presenting CPA, I also present CPB, which builds upon CPA by incorporating the concept of block building, which is a technique used in many non-exact or heuristic algorithms for container loading. And then I'll also finally present computational experiments to compare these new constraint programming models with existing model formulations of container loading from the literature. So do a comparison of sorts. And I'll start with CPA, which is relatively simple. So I'll just mention that it's based on the constraint program model developed by Martin for the 3D open dimension problem, which is a different cutting and packing problem, but it's not too hard to translate to the container loading problem by making some changes. So yes, before I actually start defining variables and constraints and the objective function, I will just define two sets preliminarily. So first of all, I define I, the set 1 up to n. So this is a set of box types. Each element of I corresponds to a different box type. So, and then for each value of I in this set, I will define Ji, which is a set with Di elements. Now remember that Di is the number of boxes available of type I. And therefore, each combination Ij will correspond to a single box of type I. So since there are Di boxes of type I, then this set will enumerate over all of them. And I will use box Ij to refer to the box corresponding to the indices Ij as shorthand. Okay, so having defined these sets, I will next define the variables, the decision variables that we need. So I'll just mention that for all of these decision variables, I'm using I and J and Ji as indices. And then for the decision variables here that require a second pair of indices, I prime is in I and then J prime is in J I prime, as you would expect. So for all of these, we define the following decision variables. So for each pair Ij, I define Sij, a binary variable, which is 1 if box Ij is in the container, and then 0 if it's excluded from the container. So as we mentioned at the beginning, it's possible that not every box will fit into the container, so some of them will be excluded. And that's what Sij is capturing. Then we have Xij, Yij, and Zij, which are the coordinates of the bottom left front corner of box Ij. So these variables specify where in the container the box is positioned. And I also define the variables dx, dy, and dz, substrate Ij. So these represent the dimensions of box Ij after rotation in each of the 3 axes. So yes. And then bx, by, and bz are capturing whether box Ij, essentially these variables are used to indicate whether box Ij and box I prime, J prime will intersect. And if one box is to the left of another box, then this variable will be 1. And then if it's a front or below, then these variables will be 1. And yeah, if you have 2 boxes that are both in the container, then hopefully one of these will be 1, right? And then finally, these variables here determine the orientation of box Ij. So for each k from 1 to 6, Rkij is a binary variable, which is 1 if box Ij has orientation k. Yep, so these are all the decision variables we need. Again, for all the constraints, I use these indices, and I use for all Ij instead of for all I and I, J and J prime as shorthand to write the constraints a bit more briefly. So, all right. I will not go into detail about exactly how each of these constraints work, but I will talk about what they do. So, okay, so the objective function here is just recording the total volume of the box in the container, which of course we want to maximize. The constraints ensure that, so these 3 constraints, 2, 3, and 4, ensure that boxes lie entirely within the container. I will mention that xij, yij, and zij are non-negative integers. So it'll always be in the container from one perspective, and then this ensures that it's in the container from the other perspective. It doesn't go beyond the container's length, width, or height. So yes, as you can see, these can be quite complicated, but what these constraints essentially do is ensure that if you have any two pairs of boxes, ij and I prime j prime, that are different, then, and if they're both in the container, then they don't overlap. So they don't share any volume. They have to be separated on at least one of the axes. So yes, so if they're both in the container, then at least one of these separation variables will be positive, will be 1. So they are separated, essentially. And what else do we need to do? So these constraints over here. So these constraints ensure that every box is in a valid orientation. So box ij, yeah, there are 6 possible orientations. As we know, rij has to be take a value between 1 and 6. So at least one of these will be the case. And then if at least one of these conditions will be the case, and whichever one it is, then that'll determine what dx, dy, and dz has to be. And yeah, this guarantees that. And then this final constraint over here is saying if there are any orientations that are not allowed, then we can't have that orientation. So that enforces the orientation constraints at the end. Okay, and these are the domains. So Sij, Bx, By, Bz, and then the R variables are all binary variables. These are positive integers determining where each box is positioned in the container. And then these are the dimensions of each box. So there are 3 possible values because it's just rotated from Li, Wi, and Hi. So yes, so these are the domains. Okay, so that's the CPA model. And then we'll also move, so that's quite straightforward relatively compared to the CPB model, which builds upon it. So yeah, focus. So the CPB model extends the CPA model by allowing the formation of blocks, which are made up of multiple boxes. Yes, so each box in a block is identical. It's in the same orientation as each other, and they are arranged in a grid formation. And altogether, they will form a larger rectangular cuboid, which we call a block. So by using blocks, we're able to position many boxes of the same type simultaneously, and there are no gaps between them since they're all packed tightly. In fact, you'll find that to ensure that boxes do not overlap, we only need to check that distinct blocks do not overlap, because it's automatic that boxes in the same block will be non-overlapping because of the grid formation. And so all we have to check is that 2 boxes in different blocks do not overlap, but that's the same thing as checking that different blocks do not overlap. Okay. And I'll just mention that this block building technique, or just using blocks in general, is quite common in a lot of heuristics for this problem, for the container loading problem, but such as the state-of-the-art beam search-based algorithm proposed here, but it has not previously been applied to model formulations of the problem or any other exact methods. So this is quite new, I guess. Okay. So we will define the same preliminary sets, I and then Ji, a set with Di elements. However, in this case, each pair Ij no longer refers to a single box. Instead, it refers to a block consisting of boxes of type I. So yes, now we use block Ij to refer to the block of boxes of type I corresponding to indices Ij. Now, I will mention that blocks do not necessarily actually contain any boxes, so it's possible for blocks to be empty, and in fact, it's very likely that they would be, right? Because since there are only Di boxes of type I, if one of the boxes Ij contains more than one box, then some other block will have to contain 0 boxes for it to all add up to something less than Di. So why do I still initialize Di blocks? Because of type I, because that preserves all possibilities, including the possibility of placing each blocks individually in its own block. So by defining DI blocks, I'm making sure that all feasible solutions are still feasible in this block formulation. All right, so I guess I'll talk about variables and objective and constraints again. So just briefly, so X, Y, Z do the same thing as before. This time they talk about the coordinates of the block, bottom left front corner. Dx, dy, dj are the dimensions of a block, sorry, a box in the block. So since all boxes in the block have the same orientation and the same type, same dimensions, then yes, it can be any of them. Just, yeah. All right, so, and then these are the separation variables, which govern whether one block is separated from a different block in each of the three different axes. And these are the orientation variables, which check which orientation the boxes in block ij have. So they pretty much have the same meanings as before. These are the new variables, I guess. So we no longer have the binary variables Sij, which determine whether a box is in or out of the container. Instead, we have 4 integer variables. So nx, ny, nz, and n. So n tells us the total number of boxes in the block. And that could be 0, in which case the block contains no boxes, or it could be non-zero. And then nx, ny, nz tell us how many boxes there are in each of the 3 directions. So nx is the number of boxes in direction x and so on. So yes, and ny is the number in y direction, and nz is the number in the z direction. Okay, and then lx, ly, and lz are the final variables we need or want, and they represent the dimensions of the entire block. So in each of the 3 directions. So they will be used to check if different blocks overlap. Okay, so I added a picture here and a figure to kind of explain the various variables that come into play for defining blocks. So this is just projected to 2D, but you have the x and y axes. So this 0 up to L and 0 up to W is the entire container. And then you have xij and yij are the bottom left coordinate or the bottom left front coordinate, so of the block. And then dx and dy are the dimensions in each of these in the x direction and the y direction respectively. Lx and ly are the dimensions of the block, so they go the whole way. And then nx and ny count the number of boxes you have in each direction. So in this case, nx would be 1, 2, 3, 4, 5, 6, 7, 8. And then ny would be 6. And the total number of boxes, ignoring the 3rd dimension, would be 8 times 6, which is, if I'm doing the math right, 48. Yeah. Okay. So that's n. Nij would be 48 in this case. Okay. So that's that. So again, the objective function is still the same thing. We need some additional constraints now to take into account blocks. So this constraint over here, constraint number 23, just essentially counts the total number of this should be boxes in each block. And constraint number 24 ensures that only DI boxes of type I are used. So this was not necessary in the CPA model because we only had DI possible boxes and each box is just 1 box. But here we have DI blocks, but each block can contain more than 1 box. So it's important to make sure we limit the number of total number of boxes of type I as to DI. We do need a constraint in this case. Okay. L, X, Ly, Lz. So 25, 26, 27 are just measuring the dimensions of the block in terms of the number of boxes and then the dimensions of the boxes. Okay, and then these ensure that the block remains entirely within the container. And if the block is within the container, then every box in the block will also be within the container. So that's good. We also need to make sure that any two blocks do not overlap. If two blocks overlap, then there will be two boxes that are overlapping. So it's important to make sure that they don't overlap. Okay, so as with the CPA model, we need these constraints. In this case, we're using L instead of D here because L is the dimension of the blocks. Okay, so we still have the same rotation constraints as before, ensuring that every box is in the valid orientation. And we also have the domains of all of the variables. So you see that in this case, we have a lot more integer variables because of the N and the L variables that we are using now, but the other variables remain the same. Okay. So those are the two models, which I didn't go too in depth into every single constraint, but I think hopefully I presented the overall idea of them. All right, so those are the models. And now we want to see, are they actually useful models? Are they good? How do they compare with existing models, for example? Okay, so how do we test them? So we tested them on instances from the literature. And in this presentation, we will present the results obtained for the BI instances. We also tested them on some other instance sets, but in this talk, we just talk about the BI instances, which are the most widely used instances in the literature for evaluating algorithm performance in general for container loading. So yes, it's quite logical to use BI instances. And in fact, there are a lot of BI instances. They consist of 1,600 instances, so quite a large data set, organized into 16 classes of 100 instances each. So they go from BR0 all the way up to BR15. So yes, quite various. And then I'll just mention that BR1 up to BR7 were generated by Bischoff and Radcliffe, while BR0 and BI8 up to BR15 were generated by Davies and Bischoff. So these were generated earlier, and then these were generated later. So what other properties about them should we talk about? So the number of boxes, the number of different box types increases progressively across the classes. So BR0 consists of homogeneous instances with only one box type, identical boxes. BR1 has 3 different box types, and then up to BR7 is 20. So these are weakly heterogeneous instances according to our arbitrary definition of weakly heterogeneous. And then BR8 up to BR15 have between 30 and 100. So that's what we would call strongly heterogeneous. Okay, so quite a lot of instances with various different boxes. Okay. So before I continue, I will mention that there's this paper by, there's this computational study, which from 2019, which compares several existing exact methods for solving the container loading problem. Tony was actually part of the group working on this, and then those exact methods were mostly mixed integer programming model formulations, which are solved using Gurobi or Cplex, but there was also a branch and bound method as well. Anyway, yes, so what this computational study found was that the best performing models for the BI instances are the MIP models adapted from Zai in 2014 and then Chen et al. In 1995. And apparently they would perform the best using Gurobi as opposed to Cplex. So yes, I say adapted because the models developed here were not actually originally for the container loading problem. I believe they were for the 3D bin packing problem or some other similar related problem, but it's quite easy to adapt from the bin packing problem to the container loading problem. So that's not too much of a problem. Okay. So what we will do is, since these are the two best performing existing exact methods for container loading, or for at least for the BI instances, we will compare the performance of CPA and CPB with them. To have the fairest possible comparison, we will use state-of-the-art solvers for all models and try to keep their settings relatively similar. So in this case, we will use Google OR-tool CPSAT for the CP models, CPA and CPB. And then for the MIP models, we'll use Gurobi 10.0.1, which is also a up-to-date solver at the time of writing the paper. So what other settings do we use? 3600-second time limit, 64 GB memory, and 4 workers. All other solver settings are the defaults. Okay, so yeah, change as little as possible. And then also, we performed the experiments using the Spartan high performance computing system here in Melbourne University. So yes, so they were all performed on the same system. Okay. All right. So I'll just mention before we move on that the BI instances are very difficult. In fact, they are too difficult to solve to proven optimality. It's not realistic to expect that we can obtain a certificate of optimality within a reasonable time frame. So instead of doing that, we will follow the approach used in the computational study and just report the best solution obtained by each model solver within a given time limit, which was 3600 seconds. Yeah, so this is actually essentially the lower bound of the model. Okay, so here is the table of results for all 4 models. So as you can see, the Xi model is overall performing the worst, although it's a little bit better on BR0 compared to the Chen model. But as you can see, CPA and CPB both significantly outperform the MIP models in terms of the best solution that can be found within 3600 seconds by quite a large margin, actually. So these are just individual classes. But in fact, if I move on to the next slide and present the averages for homogeneous instances, which are just BR0, you can see that CPA is about 82, and then CPB is about 90% volume occupancy on average. I should mention that every entry in the table is just averaging the volume occupation over all 100 instances in the class. And here it's averaging over the 700 instances in BR1 up to BR7 and so on. Okay, so for the weakly heterogeneous instances, you can also see that our constraint programming model significantly outperformed the MIP models, and same for the strongly heterogeneous instances, BR8 up to BR15. In terms of comparing the 2 constraint programming models with each other, we can see that the block building approach, which was CPB, provides a significant improvement for homogeneous and for weakly heterogeneous instances. However, for strongly heterogeneous instances, as you can see, the difference is relatively small. And in fact, if you go back to the previous slide, you can see that for BR15 instances, which are the most strongly heterogeneous instances, the block building model actually does not provide improvement over just the baseline constraint programming model. So while the gap is quite large for homogeneous and for weakly heterogeneous instances, there's no gap for strongly heterogeneous instances or smaller gaps. So I guess the question would be, why might that be? And I think it's quite easy to see when you present them visually. So for example, let's take this case of the first instance in the BR1 class. So these are weakly heterogeneous instances with only 3 different box types. And because there are only a few box types, and then therefore a lot of boxes of each box type, then we can form these very large blocks using CPB where, there are just many boxes in each block because there are a lot of boxes available of each type. So as you can see, because of these blocks, we can form these very efficient packings and occupy a lot of volume. So in this case, we got 93.38% occupancy for this particular instance. Compare it with CPA, which has to place 1 box at a time, and it gets 87.84%. I'll just mention for the color scheme, I colored all of these boxes differently just to emphasize the fact that they're all placed 1 at a time individually. So whereas in this case, I colored every block differently. So boxes of the same color are in the same block. So yeah, you can see here, for example, the blue box up here and then the lime green box over here, they're actually the same dimensions and orientation, but I colored them differently to emphasize that they were placed separately. Okay. So that's for weakly heterogeneous instances. What about a strongly heterogeneous instance? Well, it's quite a different story. So this will be an example. for this particular example, we actually find that CPA gets a better solution. So this is a instance from BR15, the most strongly heterogeneous class. And you see that in the CPB model solution, there are some very small blocks. Like here, there's a block containing 2 boxes, and then here there's a block containing 2 boxes, and here as well. But these blocks are not able to help us significantly with improving the volume occupancy. And in fact, we get a worse solution. And in terms of why it would be worse, I would assume it's because we are just defining so many more variables into the model and for relatively little gain. So the model is just so much bigger and more difficult to solve and obtain good feasible solutions. Yeah. So what can we conclude from all of this? So we found that the CPA and CPB models do significantly outperform the existing best exact methods from the literature. So that's quite good to see. And in fact, the CPB model, which uses the block building technique, obtains better solutions than the CPA model for most instances, with the exception of some very strongly heterogeneous instances. But for most instances, the CPB model is able to further improve upon the CPA model, which is itself a significant improvement over models from the literature. Okay. Yes, so that's good. So that's kind of the main result of my paper, of our paper, but we also did some other things as well in the paper. So I'll just so I didn't include them all in the presentation because in the interest of time, I wasn't sure how long this will take, but yes. So what else did we do? So we also investigated the performance of models over time. So we gave them all a 3600 seconds or 60-minute time limit. But what if we only gave it 1 minute or 5 minutes, 10 minutes? Would it have significant impact on the relative rankings of the models? We found that it pretty much didn't have much impact. For most instance classes, the CPB model was still the best, even with a very short time limit and so on. At least for BI instances. For LN, so we also consider the LN instances, which is a set of only 15 instances, so it's quite small. They were proposed a very long time ago in 1992, but I guess the more interesting thing about these instances is that most of them can actually be solved to optimality. So they are quite useful for allowing us to assess models instead of by the best feasible solution we can find in a time limit, by how long it takes for the solver to find an optimal solution and obtain a certificate of optimality. So it's kind of a different problem with the airline instances, but yeah, so that's also part of our analysis in the paper. Part 3 was we also formulated vertical support constraints, which I briefly discussed earlier. So essentially they ensure that boxes are supported by something underneath it, either the bottom of the container or the tops of other boxes. So I explained how you can formulate them in the constraint programming models, CPA and CPB, and also ran some experiments with them. We found that the solutions we obtained were really quite not very good, but at least we demonstrated that theoretically we can model these constraints even if the solutions obtained are quite poor. But yeah. Okay, and then in the paper, we also included an instance space analysis. So as you might remember, the title of my thesis actually began with instance space analysis, but in this talk, I didn't really talk about instance space analysis much, unfortunately, but yes, that is part of the paper. We did an instance space analysis comparing different models for the CLP, container loading problem, to further explore their strengths and weaknesses across various instances. So we did find, for example, earlier that the CPB model was the best model for the vast majority of instances. However, by performing an instance space analysis, we can further just investigate exactly what properties of instances make block building worthwhile, what properties make it not worthwhile, and so on. And also we can explore the diversity of our instance sets and so on. Yes, so unfortunately, I don't have time to present all of these, but they are part of the paper, which hopefully one day will be published. But yeah, fingers crossed on that. Okay, so these are the references that I refer to in this talk. So yeah, so here's okay, that and that. All right, and thank you for listening.